Okay, I think we are here. Just to be okay, I think I don't hear anything. Okay. Perfect. On the other side is there. Can you hear me okay? You're okay? Okay.
Yeah, I'm okay.
I'm gonna share real quick back again the thing. And then okay, that's the wrong one. That's the one. I'll use my trusty iPhone to tell me the time.
Yes.
It's the official timekeeper. You'll be assimilated. What we can do about it. Anyway. You guys started already the semester, or you guys...
Yeah, we start in regular school starts in mid-August, and university students start beginning of September. So it's already very much fall here. So.
Yeah, for us, we started actually at the end of the fall, I think, for some reason. I don't know why. Okay. We're a little behind the times. Okay, so I think it's 3 o'clock. So I wanted to welcome everybody once again to the online SPICE and SPIN+X seminar series. We had a bit of a summer break, and I wanted to thank you all in the name of myself that I organized primarily with the help and aid of Alexander Muck, now in the Münster, Libor Schmekel now in Dresden, Angela Wittmann here in Mainz, and Karin Ebersot now in Duisburg, but also in collaboration with the SPIN+X Collaborative Research Center that is led by Martina Schliemann, Burger Hillebrands, and Kaiserslautern, and my dear colleague Matthias Chloe here in Mainz. As you know, this is the webinar format. Please ask your questions or write them in the chat, and I will monitor them to give you the floor later on to as a speaker. And please check regularly our schedule, but of course you will get a notification if you're in the email list of when they're available, and anytime, immediately after the talk, they will be available on the YouTube channel to review and see all the time. Today is a pleasure to welcome Annica Black-Schaffer from Uppsala in Norway. She has a strong, of course, besides they've been in Uppsala, she's had a background in the US and Lictor University when she began it all a while ago. But she worked a lot on unconventional superconductivity. So this is the idea of a SPICE that we bring other communities that typically will not talk spintronics, but really to think about how these things are connected, and she connects precise and conventional superconductivity with topological matter, graphene, and as you can see, that diversity that we crave here in SPICE has numerous awards. It's a long list in there. I don't think I'm going to go through all of the awards. It's just to say that we are in it for having a wonderful talk and a wonderful speaker. Then also glad that she's going to be here next week in the workshop that we're organizing. And with that, I'm going to stop sharing, and I'm going to give you the floor, Annica, so maybe you can start sharing you, and I will put myself down for a bit and then come back if I need to, otherwise. The floor is yours.
Good. Does it look good on screen?
Yeah, it looks great.
Yeah, okay, perfect. Thank you. Yeah, thanks so much for the very kind introduction, and I'm very happy to be here. My background is primarily in superconductivity, but I thought that today would be interesting to talk about some work where we're taking a superconductor and put it next to an altermagnet. And we had some ideas that was going to probably generate a lot of interesting physics, and we were right. We found a lot of what we thought was interesting effects. I was hoping to share those with you today. And just to put things right, Uppsala is actually in Sweden and not in Norway. Small side remark. Yes, it's okay. It's a little sensitive between Sweden and Norway.
I fully apologize.
Friendly fire. So, let me see if I can move. Yeah, there. So I will start with a short introduction to altermagnets. Probably a lot of you know more about that than I do, but just to set the stage and see what I'm using, and then also how it interfaces with superconductivity, and then dive straight into our results. So I'm going to tell you a whole bunch of different phenomena you can get when you combine superconductivity and altermagnets. We can get both finite momentum and field-induced superconductivity. So there's a superconductivity that doesn't exist when you have zero magnetic field, but you get it at higher magnetic field. And I'm going to show you that it's actually very easy to get a superconducting diode effect in this material, and it's even perfect. So it's like 100% efficiency, which as far as I know, it's unlikely. Well, it's hard to find in other places, and also why we get it in this material. And then talk a little bit about that you need to be a bit careful about what sort of superconducting pairing you consider in altermagnets, because it does have this, as you may know, the sublattice structure, and that actually limits the simple model you can use when you study this. And then finally, if I have time, I hope I will have that. I'll talk about some results we have, and we did some ab initio modeling on strontium ruthenate, which is an intrinsic superconductor, and see how close it is to actually also be an altermagnet. So there I find the real material where we might be able to combine these two effects. But before that, let me just actually introduce the person who did all the hard work. So that was done by Damala Chakraborty here in the picture here. He was a postdoc with me, but moved into a faculty position in India. But we continue to work a bit on this topic. And the work on strontium ruthenate was done primarily calculation by Carmine Oteri, who's in MagTop in Warsaw, and also with collaborators in Italy. And of course, without funding, none of this would have been happening. So we are grateful for that as well. Okay, so let's dive straight into the introduction. This pictures you've probably seen before, but just sort of trying to position what the magnet is. So in a ferromagnet, you imagine the simplest possible ferromagnet, at least, that you have the same magnetic moment on every site in space, as in the picture here. This will give you some spin split Fermi bands, and if you put the Fermi surface, so the Fermi surface around here, you can even get a Fermi surface. It just have one spin species, so it sort of look like S-wave. It doesn't have much structure in spin space. And then we have, of course, the other type of traditional magnetism, is antiferromagnetism, where you have different magnetic moments on neighboring sites. So this blue is spin up, and red is spin down, because of this being. If you split the spin and do a translation symmetry, you recover the structure, and therefore you have a spin degenerate band structure. So you actually don't see any magnetic moment on the Fermi surface like this. And then we have the altermagnet sort of in between here, where you take this structure, I like to think about it, this antiferromagnetic structure, and you rotate the blobs a little bit. So you have some rotation here on the blue ones, and here it's a 90-degree different rotation on the red ones. And that means that they're going to be a little bit in between the ferro and the antiferromagnetic state. So you have, in most places in the Brillouin zone, you have spin split bands, but there are some places where you have a spin degeneracy. So now if you cut an energy somewhere, you can get very easily a Fermi surface that looks something like this. And in the simplest altermagnets, it would be some even symmetry situation. So here is, for example, a D wave structure, but you can also have G and I wave structures. So we were sort of fascinated by this concept, as I'm sure a lot of other people are as well. And we were thinking, okay, so with our background superconductivity, what would that mean then for superconductivity? And of course, you shouldn't just think about combining different physical effects if there's no chance of finding it in nature. But there are some proposed material that are proposed to be altermagnets, and we know they're superconducting if you at least do a little bit with them. So lanthanum copper oxide is proposed to be an altermagnet, and it is a parent compound of a cuprate. So if you dope this with holes, you will get superconductivity. As I'm going to show, the strontium ruthenate is very close to being an altermagnet, we think, and that is an intrinsic superconductor. So I think it's reasonable that we will probably find something that is an altermagnet and have superconductivity. You can also think about this happening engineered structure, where you say we make a heterostructure, you take an altermagnet and you proximity couple superconductivity to it with some, say, conventional superconductor, and then we will get in that sort of junction in between them, we will get both effects. And what I'm going to talk about today, I'm going to primarily sort of a simplicity look, like I have both effects in the same material, but you can think of this happening in a heterostructure too. Okay, so why would you expect this to be interesting to look at superconductivity in an altermagnet? Well, for that, we just need to understand a little bit about what superconductivity does. So in a simple metal, I plot the Fermi surface here in the orange line. Superconductivity is take an electron at K with spin up and pair it with an electron at minus K with spin down. This is the traditional BCS pairing. I'm also going to just call it the zero momentum pairing, because this Cooper pair that I get when I pair this electron with this one doesn't have a net momentum. K minus K is 0. But we know that we can sometimes get superconductivity into a ferromagnet as well. But then something slightly different happens, because now if I want to pair, say, an electron, if I want to insist of pairing with spin singlet, I take an electron at K, and to find its partner at spin down partner, I need to be at minus K and then with a minus Q, so it's shifted in K space. So now I end up with this Q at being a momentum that is actually a momentum of the Cooper pair, or you can also think of it that the Cooper pairs have a finite center of mass. And this sort of pairing has been known for quite some time to happen at, or been sort of worked through a long time ago to happen if you take a conventional superconductor and you apply an external magnetic field. Then you spin split your Fermi surface, and eventually, so this is trying to sort of indicate an increasing spin splitting with an external magnetic field. You start with the BCS pairing, so it sort of resists and it can pair K to minus K, but it's not so good. So eventually it breaks down, and you do this finite momentum pairing in a range of parameters until the field is so strong that also finite momentum pairing doesn't work, and then you enter the normal state. So here you fully kill superconductivity, but you have this regime here with finite momentum pairing. And as I said, this has been worked through many years ago from the 1960s. It's often called as FFLO pairing, but it comes from Fulde and Farrell, who consider it a superconducting state. So if you have this modulation with Q, you can get the superconducting state that has its phase modulating with this Q as you go through real space, or you can have a Larkin-Orishnikov state, an LO state, where instead the amplitude is modulated, or you can have both of them, and it's often just referred to as some sort of FFLO state where you modulate the phase. So we know what happens in the metal and the ferromagnet sort of conceptual, and then the question is, of course, what happens in the altermagnet. So in the altermagnet, we have the Fermi surface, as I said, where you sort of have an even symmetry spin splitting. So here we have, say, one spin species is allogenated this way, and the other one the other way, and you see this particular one has a D-wave symmetry. And the question is, what sort of pairing do I get? Because you can imagine if you pair here close to the nodes, you will get the BCS pairing, it's spin degenerate. But if you pair here close to the antinodes, it very much looked like a ferromagnet. So the question, will I get then this FFLO state in this case? So we set out to say, okay, let's just see what we can get. And the result was this phase diagram. So this is what I'm going to get to in a couple of slides, where I'm going to turn the altermagnet strength, but also an external magnetic field. But let me first explain, of course, how we got there. So we set up a very simple model for the altermagnet. And since we consider superconductivity, it's a low temperature phenomena, and it happens close to the Fermi level. So we can consider a very simple model for the altermagnets. So that we have here. So first we have a term here that's just going to give us an altermagnet band structure, and more specifically an altermagnet Fermi surface. So here's this D-wave spin split Fermi surface that we get by tuning this TAM, is sort of regulating how much this altermagnet splitting is. Then we're going to also tune with an external magnetic field to see if that changes things. And then we have the superconducting pairing here, which we treat within mean field theory, as we usually do. And we are going to so with mean field theory, I create a mean field that is my Cooper pairs. And I'm going to do this with allowing for a finite Q. So I calculate this delta as a function of Q for every single Q or on a grid. And then I found for each, I found the solution, and then I minimize the ground state energy as function of Q, and then I find some optimal Q star, and that is going to be the true ground state of the system. And sometimes Q star is 0, and then I'm just in the BCS limit. And if Q star is finite, I have this FFLO pairing. So we have this. So now I'm just going to show you, I'm going to first turn off the magnetic field. So I'll show you what's happened intrinsically. And I'm going to choose an S-wave pairing. So now obviously I have to do something with this V. I have to choose this V. I have to have this V. And I can choose V to be a constant. And then which means it has no K dependence, which means in real space it's just an on-site attraction. So if you want to plot it on the Fermi surface, it just looks like this. It's just constant as function of K. And so we look for this V and we do this calculation with all Qs, and nothing particularly interesting actually happens. So we tune the spin splitting TAM, and we start from a BCS pairing, and it lasts for quite some time. And at some point it breaks down and I get the normal state. So I get no finite momentum pairing in this case. And what happens in this case is, here. So what happens in this case is that you effectively have sufficient condensation energy left at the altermagnet node. So here I plot the pair density in the Brillouin zone, and you see it's really peaked in this point here, which is the altermagnet nodes. And it turns out, this is a numerical conclusion, but it turns out that the condensation energy I get by us pairing at these nodes is enough to get BCS pairing, and you never go into this finite momentum pairing. I'm going to later in the talk actually try to convince you the S-wave pairing should not be very likely in altermagnets, and it is sort of hidden a little bit here, but to get this BCS redeem here, I actually have to have a very strong V, otherwise I essentially go to the normal state very quickly. But we're coming back to that. For now, it's just we don't get any interesting superconducting states if you have S-wave pairing. So say, okay, that was a little sad. S-wave pairing is the most common one. But then we started thinking, well, D-wave pairing is pretty common too, and especially in the cuprates. And there was this cuprate parent compound, there might be an altermagnet. So okay, let's look at the D-wave pairing too. So now the only thing we change is this V here, and we're going to now have V to be a nearest neighbor attraction, because if you do that, we get a pairing function that looks like this. So now it has it's positive in this part of the Fermi surface, and it's negative here. So you see it has a clear D-wave symmetry. So this would be the superconducting state you have in the cuprate superconductors. And now if you do exactly the same thing, we tune the spin splitting TAM, and we first get the BCS pairing, then we get the finite momentum pairing, and eventually we get the normal state. So now we do indeed get this finite momentum pairing here. So we did that, and then we also turned on the magnetic field, and this is the phase diagram we get then. So what I showed, as I said, so this to us looks a little, well, when I saw this first time, I was like, well, it looks like a little bit like a Yoda here. So we call it the Yoda phase diagram, but there's nothing really to do with that, with the green creature. It just happens to look like this. So what we I can go back. What we saw before was just the result along this lane when I turn out the magnet strength, but now I'm allowing an external magnetic field. And then going just along this line is the traditional FF phase in magnetic field, the one I talked about before. So this is well known that you go from a BCS to an FF phase, and then eventually you die out and have no superconducting state here. But what I talked about, what I showed before schematically, was going along this line. So here I go from a BCS to a ferromagnetic state and then normal. And you see this FF state is actually connected. So here I actually managed to get this FF field, this finite momentum superconducting state, without having a magnetic field, by just having the altermagnet. And what happens is essentially is that the nodes of the altermagnet and the superconducting line up, and that is when you can get this finite momentum pairing, because the superconducting state doesn't want to pair at these nodes, and that is where you also would have the BCS pairing. So it's sort of favoring the finite momentum pairing in this region. Well, it's favoring pairing here, which is the finite momentum pairing. So that was sort of the basic of this phase diagram, but then there's the whole issue with this ear. And that was very surprising to us. Like, why do I get that? Because in particular, I can go along a path here. So I have an altermagnet here, and then I turn off magnetic field, and I stop with something that's not superconducting, and then I actually reach a superconducting state. And it's very unusual that a superconductor appears when you turn on magnetic field. It's usually the other way around. It dies superconductivity. So we were initially very surprised with that, but it turns out that you can actually understand this quite easily by looking at the Fermi surfaces. So if you start with the Fermi surfaces down here, this is what we had before, and then you crank up the magnetic field, and you see the two Fermi surfaces will deform in different ways. So you go to a bit more deform like this, and eventually you're going to have the two Fermi surfaces overlap here. Just as it will always happen when you turn off the magnetic field in the structure. And what happens then, if you look at where the pair density is that exactly in this green region here, then we get pair density in these regions where we have overlapping Fermi surface. And it's a rather substantial part of the Fermi surface compared to just at the nodal points we had before. So this is a reasonable stable BCS regime actually here. But eventually you tune, this orange line will go beyond the blue line, and that's when you enter the FF phase, and eventually it's so much a ferromagnetic-like structure that goes into the normal state. So that shows just here that we can get a lot of interesting physics when we combine superconductivity and altermagnets. We get this finite momentum pairing. This is very hard to find, especially if you turn off the magnetic field. It exists in conventional superconducting magnetic field, and it happens when the superconductor and the altermagnet nodes align, and then they have this field-induced state, which I would say even more unusual to find. That happens at high, and I should say here everything was renormalized and nice as we theorists often do, but we could sort of do some estimate on how big this field, and this would be quite big fields, but would be probably measurable. It's not so big, it's beyond what we can produce. Okay, so that was the first thing we did, and I was like, okay, that was nice. But then it turns out that we actually found something in that phase diagram we thought was actually even more interesting. So that's what I'm going to talk about next, and that is a diode effect. So here is the same phase diagram where I color-coded the efficiency of the diode effect. So that is what I want to get to now next. So what is the diode effect, first of all? Well, a diode effect is when you have current in one direction, but not in the other direction. And the superconducting diode effect means you have dissipation-less current, a superconductor current in one direction, but not in the other direction. In the other direction, you can have a quasi-particle, a regular current, or a dissipative current, but there's no supercurrent. So there'd be a very big difference in how much current you can have. And, this quality was not great. But effectively what happens is that you in a superconductor, you get a dissipation-less current without applying a voltage. You just have a little bit of a phase bias, or just have current through the structure. And then eventually that, of course, breaks down. And when you put enough current in your superconductor, you eventually lose superconductivity, and you generate a finite voltage in the system. So it's illustrated here. And sometimes when you go back, you have sort of some hysteresis here. But what's important is when you go with current in one direction, this critical IC is different from when you go in the current in the other direction. That means that there is a regime when IC plus is bigger than IC minus, where I go in one direction, I will have current, but I will not have current in the other direction. So this has been studied a fair amount lately in many different materials, in bulk and in heterostructure and so on. And it requires that you both break time reversal symmetry and inversion symmetry. So it's rather restrictive in that sense, but there's many systems that still will have this. And then generally, and if they are superconducting, you actually find the superconducting diode effect. And is it both before us shown in this nice paper that the FF state are actually natural candidates to have a superconducting diode effect. So we know that already when we set out, and it's because they do break time reversal symmetry and inversion symmetry because they modulate their phase. And you look at the sort of important operational quantity here is the efficiency, where you take the the current in one direction minus the current in the other direction, or the critical current in one direction minus the critical current in the other direction, divided by the average, to see how good this is. And that was, at least when I made this slide a while ago, often sort of, it could be high, but it was not up to 100%. So we didn't have, in 100%, of course, we mean that you have a critical current in one direction and nothing in the other direction. So since we had FF state, we set out and we calculated this effect. So just to repeat what we did, so we started with the spin singlet D-wave pairing, because that's what we needed. We had a self-consistent solution for every Q, and we found a ground state, a Q star. That's exactly what we did before. But now we extracted the current. So we explicitly calculate the current in the system for each Q. And the current in the ground state needs to be zero. This sort of, there should be no current in the ground state in the system. But at other Qs, you can have a finite current. Effectively, it's a Q that drives the current in the system. And the maximum current I will have in either direction, positive and negative, will give you this efficiency. So we did this, and then was this diagram that we found that I already showed you. So here we tried for every little blob, we calculated the currents and we extracted the maximum currents in both direction, and from that the efficiency. And you see it goes from being negative to being positive, and most notably it actually reaches 1 along this line and for some points here. So I like to try to explain to you what is happening in the system. So I'm going to look at these various points I try to indicate here. Yeah, so you have a large efficiency, and it's even 100. So first we look deep in the FFA, so that is these 2 points, this point and this point. And what I'm going to plot now is first the energy landscape as function of Q, and then the current we calculate. So the energy looks like this, and this is the ground state, the lowest energy, this is Q star. And then we calculate the current. So the current is calculated here, and it's 0 there, so it confirms that this is indeed the ground state. But we also know in a superconductor, you would have the current should be the derivative of the total energy of the ground state energy as function of Q. And we do see that here, that this curve here is the derivative of this curve. This was not how we extracted this curve. So this is just sort of a visual confirmation what we're doing is correct. So now if you look at the star region here, you see that, well, if you look at this curve, the derivative is higher on this side. And then lower the maximum on this side. So that means the current is going to be more in this direction, the negative direction, the positive direction. Here I normalized it, so it reaches -1 as most, and it goes up to about 0.4, so efficiency -0.4. And very similar in this square region here. So quality of the same behavior throughout this FF region. Yeah, so then we took, okay, that's nice, we can explain those green regions, but what happens in this red region? So let's focus on those. So first, if we focus on this region here, so it has a high efficiency, but it's not quite 100 yet. So here is the energy landscape here. So here is the minimum. And if you take the derivative of this, it's going to be reasonably high on this side, so higher current on the positive direction. And on this side, it goes from a minimum to a maximum to a minimum, but it's rather small curve. So it's going to wiggle a little bit, but with small current. And that is because both this FF state and the BCS state here at 0Q are minima. So that means that, it's going to be rather shallow, but it still wiggles. The derivative still wiggles between here. The really interesting point happens here at the diamond region, because what you get here is you have the minima here, which give you the 0 current, and you have a rather large slope here. So you have a large current in this point here. But now the FF state is a minima and the BCS state is a maximum. So this is a different FF state, as I also indicated with a little prime there compared to here. And if you go very, very close to this transition here between the FF state and the BCS state, you're just going to flatten out this landscape completely here. So the BCS is going to have the same energy as the FF state. That's sort of the definition of transition between the two. And at that transition, then I'm going to reach the maximum efficiency. I'm going to be able to carry current in one direction and in the other direction I can't carry the current because my energy landscape is completely flat. And that's how I can reach 100%. Now, technically this point was, yes, I reached 90%, but if I go even closer to a transition, this point is just going, this eta is just going to go up. Okay, so that was nice. You know, we found very high efficiency, but at that point, I think had not been found before. And then the question was, okay, were we just lucky, or will this happen? But then we realized that this was actually more or less a topological feature of the system, and it has to do with this Fermi surfaces again. So here I plot, well, first of all, in the red dots, I just plot all the points we extracted where we had a very big efficiency. And then I plot on this side of the blue line, I have a nodal Fermi surface. And on this side of the blue line, I have this nodeless Fermi surface as I tune the magnetic field. And you will always go from nodal to nodeless when you tune the magnetic field in altermagnet. So you will always have this transition. And this is the transition you need to have to get very high superconducting diode effect. So this is, since this nodal to nodeless transition is protected topologically, we will guarantee to have these large regions, assuming, of course, that you have superconductivity in your altermagnet. Otherwise, well, but otherwise, of course, you won't have a superconducting diode effect. Okay, so that was a short summary of this work. So we showed that you have a superconducting diode effect in altermagnets, and it's large throughout the whole superconducting region, but you can even get a perfect diode effect in some regions, and it's protected by topology. So it will be there even if you make a more complicated model of your altermagnet and so on. Good. So far I've been telling you, okay, I couldn't do S wave, so I went to D wave, and you could think maybe that was a little restrictive, and why did I do that? And after we finished that, we came back and said, okay, really, why didn't it work with S wave? Numerically, we really saw that didn't, and we realized that there is actually a rather strong constraint on the superconducting symmetries. And I should say they're coupled to the model we were using. So if you have, an ab initio model, you wouldn't maybe find this. But in the simple model we were using, there are actually these constraints. So let me just go through those and try to explain to you why they were there. So here's another cartoon of the altermagnetic normal state. So I have a sublattice, A and B. And on A, I have, say, upspin. And on B, I have downspin. I'm trying to indicate with this diamonds that they have a different crystal structure, local crystalline structure. And if I want to model this reasonably carefully, I should do a model where I have the A site that can be spin up, and the B site that can be spin down, and A that can be spin down, and B that can be spin down. So I get sort of a 4x4 at the sort of minimal model I can get. And then you would sort of model the altermagnet like this, that you have the spin energy dispersion. So you just assume I have just a simple, say, I'm on the square lattice and just simple nearest neighbor hopping that doesn't feel the spin and it doesn't feel the sublattice. Then the altermagnetism comes because you have a crystal field splitting that doesn't feel the spin, but has a different sublattice orientation. That's why I have those different diamonds here, right? And then I have an exchange field that is both sitting on sublattice and spin, both spin and sublattice structure. And if I do that, and then I plot the band structure, and I'm in the regime where this J is very big, I get the band structure very much separated. So I should have 4 bands. I have 4 bands. But if J is big and I have a Fermi surface here, it's just 2 bands that are active. It's the A up and the B down band, these 2 bands. And now I can, of course, write then a little smaller Hamiltonian. It's always nicer to work with smaller Hamiltonians. It's easier. We just have these two bands. So now I have A up and B down. And this was really the Hamiltonian that I showed you before, that I used before. I had a kinetic energy that was not sensitive to spin or sublattice. And I had one that was sensitive, that had this altermagnet splitting. But know that this S operator, this Pauli S here, is not the sublattice, it's not the spin, it's a combination of spin and sublattice. And that is what's the key for superconductivity, because if I think of superconductivity in real space, which I always can do, I can always take my K space and Fourier transform to real space, then that is going to put limitation if I really use the simplistic model or the altermagnets. If I use this model and say, okay, I'm going to do spin singlet pairing, it's really just this Pauli matrix involved. But if I use this one, I have to be careful that this actually encodes a sublattice structure too, which if you're not, it's easy to forget that. And I honestly did the first part of this talk essentially forgetting about this. So then I said, okay, let's think about this. What does it mean this in the simple two-band model? So let's say, assume we want to have spin singlet pairing and we want to have S-wave symmetry. That means it's sort of technical form factors. One has no structure in momentum space. If something has no structure in momentum space, it's fully localized in real space. It's an inverse Fourier transform. It means it's on-site. But if you try to do on-site pairing in this two-band model, that's not really going to work. I'm going to do spin singlet on-site pairing because spin up sits on A site and spin down sits on B site. I cannot do up and down pairing on A alone or B alone. So this is why it's really hard to get on-site spin singlet pairs, which means they will be very hard to get conventional S-wave pairing in an altermagnet at this model. And that was before I did show you some result. We could calculate it, but we had to really crank up the interaction strength to get it. And of course, if you crank up interaction strength, you get more bands involved and you can do pair and it doesn't live very close to the Fermi surface anymore. So you can artificially get pairing, but if you assume superconductivity is happening at a low temperature, you will not get, low temperature, weak interactions, you should not have it. Then you can have spin singlet and you can have extended S-wave. It has this form factor, so it has some structure in K space, but it doesn't change symmetry, or you have two different D waves. This was a D wave I looked before. And this, if you take and transform this to real space, they pair on nearest neighbor sites, these two. And that is all of a sudden allowed now, right? Because I can pair A up, happily B down, because that exists. So I have a spin singlet nearest neighbor pairing. So that is allowed. And that was indeed the one I used before. And that was why it worked so well, why I could get easily a superconducting state and where I also had this superconducting diode effect, as I said. One can also look at the various spin, the various triplet channels, and it turns out you can have a mixed spin triplet on nearest neighbors, but the equal spin triplet you cannot have on nearest neighbors because I cannot put the same spin species on the same site. The same species on nearest neighbors. I can put it on next nearest neighbor, but not on nearest neighbor, which is the first harmonic. So based on this, one should really think about, unless you have a more complicated band structure that's been singlet D wave or possibly an extended S wave, or as a mixed spin triplet P wave is the simplest possible simulated states to get. Okay, so that was a little story about that. I think I have a few minutes more, so I will try to show some result with. Okay, so far I just been using a model results, but we had a very nice collaboration with Carmine and Mike Top in Warsaw, where we looked into a real material, so strontium ruthenate, and which is an intrinsic superconductor. So that's why it was very interesting for us to look into this. It's still debated what sort of symmetry and how the superconducting state looks like, but we know it's superconducting at low temperature. And the idea was that maybe this is actually very close to being an altermagnet, and we wanted to see that. So why did we have this idea? Well, here is sort of the base structure of the strontium ruthenate, so ruthenate oxide plane. We have ruthenium atoms here and the oxygen here. And if one were to rotate this oxygen caches a little bit, it gets this crystalline rotation needed in the altermagnet. And the strontium ruthenate is not magnetic, but it seems to be very close to magnets. It speculates a ferromagnet, antiferromagnet, and so on. So it seems to be very close. So if one were to have a spin down on this and spin up on this, this would actually be an altermagnet. So you do need to have this oxygen distortion. And that is, if you look at the band structure of this, it is the phonon spectrum. It is a soft phonon mode. It's not an imaginary phonon, but it is soft, so it's easy to happen. And also the surface of strontium ruthenate is known to have a rather large distortion, up to 7 degrees actually, of this particular distortion. So nonetheless, at the very least, this will happen on the surface of this material. So we set out to sort of, okay, what happens if we model distortion ruthenate and we force a distortion angle, phi, so that we have that as an input. And we did DFT plus U because we wanted to capture some correlations. And then we were going to, so I'm going to show you, we took the DFT results and also made them into a type binding model to try to understand what's happening. So first we looked at single ruthenium oxide layer because it's simpler. And here is then the Fermi surface. So we use a rather large angle, and we actually have to use a large U. I'm coming back to why this U is rather large. But the effect would be there at smaller angles, a smaller U. It's just very hard to see anything. So here are the Fermi surfaces. And social ruthenate have, maybe I wrote this here. Yes, it has 3 ruthenium d-wave orbitals. They form 3 bands, alpha, beta, and gamma. And if you used to look in social ruthenate, this might be a little confusing, but that's because I have now I have extended my unit cell, so I had to fool my Brillouin zone. But here is the alpha band, this is the beta band, and this is the gamma band. And it turns out that the spin splitting is just sitting on the alpha and beta band. The one I get here on the gamma band is actually just sort of proximity induced from the other bands. So first of all, the spin splitting that we get is orbital selective. It only shows us a few of the orbitals, 2 of the 3 orbitals. And then we were saying, okay, so how can we understand this from a type binding perspective? How do we get where's the altermagnet showing up? And then it turns out that if you look at these ruthenium atoms, you get some sort of, we have some original type binding structures from ruthenate. This was done ages ago. But what shows up extra when you do this oxygen rotation is that you get a hopping between this orbital and this one. And you can understand that yourself. This one doesn't exist if the lattice is perfect. But if I rotate a little bit, I'm going to get a finite overlap between this one and this one. And that term is this interorbital term. So this is that hopping I'm trying to indicate here. And this is going to be sort of proportional to TAM I had before. And it's only there for this finite angle. Then I had a large enough U, so I got a spin splitting, and that I can just decode, and that fits just on 2 orbitals. So that is this term. So this is the Hamiltonian lives in this alpha beta band subspace. So it has a TAM and a spin splitting. And now, if you write this sort of massage expression a little bit, you have an initial Hamiltonian. This is not sensitive to spin or site, but you have an altermagnet part that comes with this rotation angle that has a term that's sensitive to the spin. And it has a site dependence too here, but it's not sensitive to the orbital particularly. And then I have a term that is the hopping that is sensitive to the orbital, but with another Pauli matrix and the site. So I have this orbital selective state. And I forget. This actually turns out to be a G wave, and it's because this one combines with the structure of this Hamiltonian actually gives you the G wave symmetry. You probably actually saw that here, right? That there was a number of lines here that made it a G wave state. So this is it doesn't give you altermagnetism in all orbitals, but just a few. Let me see. There. Yeah. So then we went to the bulk, the whole structure with the same setup. And then it turns out that you actually end up with a D-wave structure here because the interlayer hybridization actually destroys some of the nodes, but they are still near nodes. You sort of see that it's sort of less spin splitting here, but technically there is some spin splitting there. So then in the bulk, we could try to extract the phase diagram and see which phases we get. So here is the phases plotted as function of this distortion angle and the U. And there we have, and that's sort of the regime where we think the material should be in this DFT plus U calculation. You have a normal state, and then eventually crank up U, you get a ferromagnet state. But in between there, you actually get an altermagnet state here for some reasonable angles. And in U, that seems to be what people think would be the relevant U in this material. We also included, there is some spin-orbit coupling in this material. We included spin-orbit coupling in the calculation, and then we find a weak ferromagnetism. There comes some canted moments out of the AB plane through a DM interaction. So we had that too, but in the interest of time, I will not show that structure. So that we thought that was rather interesting, and then we were thinking, okay, could this have some implication for superconductivity and so on? Rutenite is this hotly debated what sort of superconducting state it is. It was for many years assumed there was a spin triplet p-wave pairing, but then people revisited some experimental data and say, no, it's not actually a problem spin triplet at all. And now I think there's a few references here thinking, well, it's probably some sort of spin singlet, but we don't know what symmetry it is. So we think they could be, if you distort a little bit, and especially at surfaces, but if you had a little distortion, you would have an altermagnet spin split that's around 1 MeV. So it's small, but one should also keep in mind the superconducting gap is like 350 micro EV. So you should, even if this is very small, you're comparing with an even smaller number. So it's very reasonable that the altermagnet state, if it happens, should influence the superconducting state in this material. There. Yeah. So as I said, the superconducting is likely a spin singlet. The altermagnets have opposite spins on nearest neighbor and next nearest neighbor sides. So what would that, if you go back to the reason we had, which sort of superconducting state do the altermagnet allow, then we can actually make some statements on what superconducting state we should have. And I should say, these are statements made under the assumption that I have a spin singlet. It seems to be what most people think it is. And I only pair intra-orbital. There is some work saying that maybe one should pair between orbital. And I only pair in these two orbital, the ones that are sensitive to altermagnets. So it is often also, so all these are very reasonable assumptions. Many people do them. Then I can have this d-wave state, the dx squared minus y squared, or higher harmonics, so the d-wave state, or any combination of them would be, the combination are not excluded here. So for example, we could have some d plus ig state, which is, I would say, the simplest possibility that seems to agree with most experiments. But there could, of course, also be some interorbital or some pairing in the other ruthenium atom, the XY orbital. But if you have these assumptions and you think it's very close to either very close to altermagnet transition or are there already, then this D plus IG would actually be the favored state based on just energetics in the system. So with that, I just like to summarize. I'll be talking about what happens if you add superconductivity to an altermagnet. You do have to work with D-wave superconductivity, but if you do, you get final momentum superconductivity when the AM and the superconducting nodes align. We have field-induced superconductivity at high field, so this is what you get when you sit out here. You can actually start with something that's normal, you crank up the magnetic field, and you get superconductivity. And we have a perfect superconducting diode effect in this FF region, very close on the BCS transition. It's hard to get conventional S-wave superconductivity in the structures. And we think the structure ruthenate is at least close to be an altermagnet, and it could have potential effects on what it does with the superconductor. So with that, I thank you for your attention.
Thank you very much. Thank you also for the 110 people that have been between Zoom and that have been watching. So now we have the talk open for questions. Please raise your hand if you have questions. There was one question here posted by Babu. It's unfortunately it may not be there anymore, but I would like to ask a question just for recording. In altermagnets, numbers are combined, as you know, with the spin rotation symmetry allows spin splitting without net magnetization. And how does this symmetry particularly affect in the planes of the strontium ruthenium oxide this possible pairing, and would you still expect this to be together? And then have
yeah, I'm not entirely sure if I understood the question. Yeah, so there is a couple of assumptions. I mean, if it's altermagnet, we know what sort of symmetry the altermagnet has. So that's established. Of course, you could argue that no, it's not an altermagnet. But if it is that, and I would say also if it's close to the altermagnet transition, you have fluctuations that will be sort of helping you with superconductivity. It's also sort of, it's a very low energy phenomena, so it could be. And then you do get, just from this argument that I gave before, these two states are the most favorable within this energy regime. So if you were to have a higher energy regime, you could have others. But I don't know actually if that was a question.
Yeah, well, he was not around anymore, so
yeah, okay, yeah, okay.
Leonie,
Yeah.
if you have a question first. I'm not sure if Leonid had a question, but if not, John Xiao.
Let me.
The question
Hello,
first.
thank you.
Oh, sorry.
Do you hear me?
Go ahead, Leonid. Go ahead.
Yeah, thank you for a great talk. I'm wondering if I would be able to go, let's say, just changing magnetic field through the phase diagram and cross from BCS to FF state. What features experimentally I would see, for example, how critical current would change? Would I see some, what type of phase transition I would see there? That's question number one. And question number two, when you were talking about, that's sort of related question, when you are talking about diode effect, which direction current will be suppressed and which direction current will be critical current will be enhanced, how that is related to crystal structure, or what direction is chosen?
Yeah, they're very good questions. I mean, obviously, you go from the normal to supercritical state. You should see that experimentally. Go into the Fermi. So I don't have a good answer for you, but my simplistic answer is that this thing to go from this BCS to this FF state is reasonably similar transition to go from this BCS to this FF state. It's sort of going from a zero momentum pairing to a final momentum pairing. If you were to be able to measure the superconducting state, how it's modulated space, it would be very clear. But I suspect there are actually I suspect there are other signatures, but I'm a little rusty on that. The which direction is, I mean, of course, it's dependent on the crystal symmetry. To some extent, you could go around X and Y, it didn't matter, so we just choose one direction, and it's going to be one direction that's positive and one is negative. I mean, to get this diode efficiency, you measure in both directions, you see it's an asymmetry between there, but in our case on the square lattice, the X and Y are the same.
But maybe related to the question of Leonid, I think he refers to that. I mean, here you supposedly you will have nail ordering and superconductivities together to have this non-reciprocity, right? So this directional will be connected to that.
Yeah, the setup. Let me see if I can. I might be answering wrong, but I think it's. So here we choose QX, but you should be able to go in QY. It might be that it changes, which is positive and negative in the QY direction, but I think you should be able to go in the QY direction too.
Yeah, but I think according to Leonid, my feeling is that it will be related to the breaking reversal symmetry from an L vector that will determine which one is the positive, more or the less.
Yeah, you might know that more than me. So yeah.
This is
yeah.
You know, yeah, I guarantee. Okay, Leonid, is that okay? We'll move on to John, maybe.
Yeah, thanks.
John, go ahead.
Okay. Yeah, very nice talk. This is John Xiao from University of Delaware. I think at the beginning, at the introduction, you mentioned, this doesn't have to be altermagnets and superconductivity happening in the same material. Heterostructure will work. Can you elaborate this a little bit?
Well, I have of course, one should probably model and make sure. I have a very simple-minded view on this Hamiltonian. We can even put on the magnetic field, I guess, saying that, okay, I need to have a band structure that comes with something, and then I need to induce superconductivity. But this V doesn't need to live in the same. So if you think of some sort of slab material, you have the altermagnets, and you put the superconductor on top, then you proximity induce the pairing potential. So this term doesn't need to live in the same. For me to use this Hamiltonian, this V can live in another layer and be proximity coupled. And one should, of course, look. I mean, there are people who look at this heterostructure, but at the simplistic level, this will be the same Hamiltonian, even having this V being proximity induced. And therefore, we think that this result should also go through there. But it's a somewhat simplistic assumption that I'm making here. Of course, it will require looking a little bit more carefully.
Great, thanks.
Okay, great. Let's see. Sorry, I don't know. Gambira, you had a question. Maybe you can just question?
Yes. Can you hear me?
Yeah, we can hear you a little bit low, but maybe louder, maybe.
Yeah, sorry, I'm in the lab.
No problem.
Thank you for a nice talk. I have a doubt that I recently read a paper, a theory paper, in which like they worked on giving a theory on having an altermagnet with the spin-orbit coupling interface, and they tell like we can generate unconventional triplets using this. What do you think? Like, will that work?
There's a lot of possibilities, and if you add explicit spin-orbit coupling from an interface, you can get many other pairing. And I should say the argument I made, or too many slides here, but the arguments I made here about which superconducting pairing I get is sort of based on if you use a very simplistic two-band model, one needs to be careful about which state you have. If you were to use the full four-band model, but it comes back from having the other spin bands sort of pushed up in energy and a real material, maybe this could be a little smaller and the Fermi level is somewhere else and so on. So it will depend. But at the simplistic level, if you are thinking of altermagnets with a two-band model, one needs to be a bit careful when you interface it with superconductivity. I guess that's my basic statement. Then real materials, this will change, interfaces, things will change. And with spin-orbit coupling, you can obviously go from a spin singlet to a spin triplet state and so on. So it could very well happen, I guess is the short answer.
Okay.
Thank you.
Let's go to, there's a question let's go to Ali Reza next, and then I'll continue.
Yes. Hello, Annica.
Hello.
Yes, good. Thank you for a nice presentation. I have a nice question about your last part of presentation about strontium ruthenium oxide. You consider it a single layer, yeah? Then, but the experiment observes superconductivity in thin film and bulk, yeah? And also there are some ferromagnetic fluctuation in thin film. But then how you connect this your result to reality?
Yeah. So we did exactly. So here the results were connected to reality, at least through ab initio calculation. So we did first do the single layer because it was just easier to sort of see what it is. And that was how we extracted the band structure. But then we did the full, so this result is actually the bulk result when we had the whole structure. And then we did, I didn't have it in the talk here, but we did extract what the interlayer hybridization looks like and why it breaks the, why I get rid of this now.
But here you consider this bulk, but you artificially add U and you didn't really compute U, yeah?
Yes. So in DFT plus U is a parameter you put in.
Yeah.
And to match up sort of, and this is not my expertise, it's really convinced, but,
No, but
he convinced me that, yeah.
This is very dangerous, yeah, because you can always add U and find magnetic instability in every material. Yeah.
And what I would say, since if you think it's strontium ruthenium, it's not magnetic, so then U should be here somewhere. And then the question is, okay, if I were to make a distortion, I can actually easily go from the non-magnetic to the altermagnet. So I would think, I'm here somewhere in the real material. But yes, U is an input parameter that I have. And if I don't have U, I miss some correlations are there. So it's tricky which U to pick, and it's not in the first principle U I put in. I have to choose it and then try to match it as well as I have. But we did try to, well, here U was too big to see the effects, but we could have a U smaller. It's just we wouldn't see anything in the plot, so that's why. But we did have the spin splitting. So we were trying to align the U with what has been used before and used to match band structures. That is as much as I can say.
Yeah, thank you very much. Thank you.
Revas, can you maybe ask a question and then we go to Olena? Yeah, go ahead.
Hello, and thank you for the inspiring talk. Could you please go back to one of your Yoda ear diagrams? Yeah, that one was.
Oh, okay. Yeah.
Whichever one doesn't really matter.
Yeah.
So I just had a naive question. So you had magnetic field and ultramagnetic strength. They are given in what units? In units of what quantity?
So here they are given in units of T. So I just got everything to be unitless. We did in the paper, and I'm very bad with remembering numbers. We were trying to translate this, what it would mean in some sort of prototype real altermagnet, and we concluded that you should be able to sit here, and that this is not a it looks rather high, but there should be altermagnets with the strength, and we should be able to tune up to here within available magnetic fields at high magnetic field labs at least, or even lower magnetic fields. I think it was like maybe 10, 20 Tesla we got to, but there are more numbers in the paper. I apologize for not remembering exactly.
If this is hopping, this is the electron scale, and so then these are all huge values.
Yeah, so maybe
I would, yeah.
From a magnetic field perspective, from the
for the magnetic field or for ultramagnetic splitting as well.
Well, the magnetic field, some of them can be pretty large, if you remember. Yeah, not all of them, of course, but some of them can be of electron volts.
There is a few constants that are missing here. I was just saying, to get this to work out in the units of energy, I sort of take out, there's a parameter here, T, that is sort of outside everything, and then I just normalize with that. So that was what it was based on there. We believe it should be reachable. I can right now, without going back to the paper, tell you exactly which numbers we put in. Sorry.
Naively, to me, it felt that these would be huge values, but maybe
yeah, there was a little bit. We actually had a referee question on that, so we went back and said, okay, can we really get this?
That would be pretty large. I would imagine it would be huge fields, most likely, which means that many things will happen before any of this happens with large fields.
Yeah,
I don't know how you would look the altermagnetic strength that easily.
So the good thing here is, of course, we could say maybe we can find a material with this altermagnet strength, but these are all self-consistent calculations. So, and we use a pair potential that was very reasonable to get a TC here. So it wasn't sort of, we didn't crank up superconductivity unreasonably high, and since it was self-consistent calculation, this is appearing in the system, so at this magnetic field. So there was a superconducting state that survived that magnetic field.
So what you mean here by altermagnetic strength is the splitting, essentially, not...
Yes. Right. So it's this very simple two-band model, right, that I have. It's just the spin splitting. Yes.
Not sure how that could be tuned, but anyway, good.
Yeah, no. A real material would sit somewhere. So you have to find this, you would have to find a material that sits here, and then you tune the magnetic field. But yes, no, this one wouldn't be tunable.
We'll discuss that next week.
Yes.
Okay, great. Is that okay, Reza?
All right. Thank you. Thank you very much.
Sure, good to see you. Then let's go to, actually, because Santanu, you had it first before Olena, then Olena. Go ahead.
Yeah, can you hear me?
Yeah, we can hear you.
Yeah. Hi, Annica. This is Shantanu Mukherjee from IIT Madras. I had actually a couple of quick questions. One was regarding this, again, the year of Yoda question. In your Hamiltonian, the way you introduce the field, is it primarily the Zeeman contribution, or do you also include the orbital effect? I was just wondering that if you have orbital contribution.
Yeah.
Okay, so I was just wondering if you have orbital contribution included, this re-entrant BCS behavior, could that line shift? Because we
were thinking about 2D, where we put the magnetic field.
Okay, perfect.
So we wouldn't have that, but of course, if you have 3D, there would be an orbital effect. We did not take it into account. Yes.
Or out of plane field. For that matter. The two. Oh, okay. So the second question was regarding strontium ruthenate. So there are these recent low energy MUSR which claim surface magnetism on these systems, right? Probably because you have the octahedral rotation, that would be the area you're looking at. They also in STM, for example, they don't seem to see superconductivity on the surface for these systems. Could that reconcile with the competition between superconductivity and maybe an altermagnetic model for strontium?
We have been thinking about this. We haven't done any calculation, partly because doing the surface is a lot more expensive than doing the bulk, but it should be doable and see, because at the surface, as I said, it will have this distortion, and it's big too. The numbers I showed before was a lot smaller. There are other proposals to what happens at the surface and why it's magnetic. I don't think, generally, if you get a magnetic state, superconductivity doesn't really enjoy being there. We saw it in the U day, you crank up the altermagnet strength too much, you lose superconductivity. So it's not surprising to me that you would get a surface that has some sort of magnetic state and it's not superconducting, and the superconductor lives in the bulk instead. It's sort of competing phases. There's, of course, one could imagine, because we don't know what's causing the pairing in strontium ruthenate, maybe it is actually, if it is spin fluctuation driving it and it's close to an altermagnet, then one should do a spin fluctuation calculation with the altermagnet fluctuations to not ferro or antiferromagnets, what's been done before. So I think that is an interesting future direction to consider for this. If you have, and I think that goes, even in the bulk, you don't have this distortion, the material is rather close. You see in this phase diagram here, even if I set a very, very small angle, I have some altermagnet. I'm closer to the altermagnet in some sense than the ferromagnet. So it's, and I don't know if that makes something, if the fluctuation has an altermagnet property, does it make a difference from the superconducting state I can get? So that's a big open question that I would love to answer, but I don't have an answer to.
Right. Yeah, that's probably an interesting question, right? If one were to do a paramagnetic fluctuation calculation with a Hamiltonian that you generate from these DFT, which what is the ground state superconductivity that comes out?
Yeah.
Because what Brian and others did, they see these S plus IS or Kivelson's D plus IG, which we have talked about.
There's many of those calculations, and
I know.
The new thing would be to put in this particular spin structure into that.
Okay. Nice. Thank you so much.
Great. Let's finish with Elena. Can you please ask your question, Elena?
Thank you. I would like to continue the question which was asked by Rivas. So can we go to your diagrams? So in fact, I wonder this TAM, we know this value for many altermagnetic materials, and this is the largest for ruthenium dioxide, and for lanthanum cuprate it's smaller, and so on. Can you show on this diagram where, for example, ruthenium dioxide is?
The short answer is no, I cannot do it here. I can, with a little bit of thought, do it, but not right here.
But how far is, or how close to zero is ruthenium dioxide? So what I would like to understand is the scale of these altermagnetic strengths. You said that the values are large, but how large they are, how attainable they are for the real materials.
Yeah, it's as I said, we were trying to approximate this, and I should look this up. I don't remember, but we looked at some of the proposed altermagnets at that point when we wrote the paper, and saw, okay, could we find this regime where this ear appeared? And we were convinced that yes, we could within this, but I don't actually remember which exact material we looked at. But I'm very happy to go back and discuss this more, but I do need to go back and look at that.
Okay, thank you.
Okay. Well, I think with this, I'm going to stop the streaming now. And then here as well, I think, in here, okay.